Greetings, Panthers. Dr. Augustine again. Hope you all are doing well. Today we are going to take a look at solutions, specifically aqueous solutions, and a concentration unit called molarity. So that would be called molar concentration. So this video is going to cover chapter 5.2 intro, cleverly named solutions and concentrations. We're going to take a look at solutions and then the definition of the words solute and solvent. What is an aqueous solution specifically, because you can have different types of solutions, but we're going to specifically look at aqueous solutions. And then a specific concentration unit called molarity, which is given the symbol capital M. And then we are going to take a look at some examples on how to use a stock solution to dilute solutions. So let's start with a couple of definitions. A solution is a homogeneous mixture . And a solution, you can have a solid solution, you can have a liquid solution, or you could have a gas phase solution. So an example of a solid solution would be something like an alloy. Bronze and solder would be two examples of a solid solution. Solder is a lead tin alloy. And liquids, some examples of this would be something like cleaning solutions, soda, tea, etc. And then a gas phase solution, it's a homogeneous mixture, so this would actually be something like air is a good example of a gas phase solution. So that is nitrogen plus oxygen plus CO2 plus whatever else, some smaller components are in air. Okay, so air is a mix. Air would be considered a solution. Lots of different liquid solutions we can come up with, and the ones I've named here, like cleaning solutions and soda, those all have water as our main component. And then alloys, we can, any types of solid solutions, we come up with different types of alloys or whatever. So we have a couple of names we use. We call them the solute and the solvent. The solvent is the component with the highest percentage. So, for example, air, the component would be nitrogen. About 78% of air is nitrogen. So the solvent would be nitrogen, and the solutes would be these other things that are dissolved in it. In these examples, cleaning solutions and can of soda and tea, water is the solvent, and then whatever is dissolved in it is called the solute. So this is the smaller components. You know, I put component, it's really components, depends on what it is. Something like soda has a lot more than just one thing in it. I mean, there's sugar dissolved in it, but there's coloring agents, and there's also gas dissolved in it. So there's other smaller components in it as well. So we call it the solvent and the solute, and those two together make a solution. Specifically then, when we have water as a solvent, which is a very common solvent, if we have water as a solvent, we call this an aqueous solution. And because it's such an important solvent, and because the aqueous is such an important system, we're going to talk about a bunch of different reactions that occur specifically in aqueous solutions. And that's kind of where we're heading in the next couple of videos. So if we dissolve stuff in a solvent, it would be convenient, or it'd be nice to be able to quantify how much of that stuff is dissolved in. So I'm just going to sketch something out here. Let's say we have two beakers. Let's say that we have two beakers, and let's suppose that they contain a solution. And let's say that the solution we have is some kind of food coloring. And let's say it's a red food coloring. Now I can't control this on here, so I'll just control this I can't control the darkness of the red that I'm drawing, unfortunately. But let's just say I could darken this one up. So I have two different containers, and one of these, there's more food coloring in this one, and there's less in this one. So we'd like a way to quantify that, and the way we do this is concentration. And the concentration is a quantitative measure of the amount of solute dissolved in this solution. Okay? So it's a quantitative measure of the amount of solute in a given solution. Now there's lots of different concentration units that you could potentially run across. But the one that we use quite often in chemistry, certainly in the first semester of chemistry, is a term called the molarity. And the molarity is defined to be the moles, and I'm going to use a little n to symbolize number of moles of the solute divided by liters of solution. There are other concentration units that we can use, but this is the most common concentration that we're going to use for general chemistry. Okay, so moles solute, that little n means moles. Number of moles of solute divided by liters of solution, that is called the molarity. Using that molarity, then we can determine a lot of other things about a solution. We can figure out if we're going to do a dilution, how do we do that? In other words, how do we get from this more concentrated one to the less concentrated one? We can use molarity to figure that out. We can figure out how many moles we have depending on what size container we take out of this, etc. So that's where we're going to go with this. Now let me just give a fundamental idea that I think some students have a little bit of a hard time understanding. Let's take this as an example of maybe we're in the South here. Let's say we have some sweet tea. Okay, and let's pretend we have a big container of sweet tea, like 5 gallons. We're in a restaurant or something, and they've made a big 5-gallon container of sweet tea. And you pour out, it's got a little nozzle on here that lets you pour out some sweet tea into your cup. So into your cup, you pour this sweet tea, and whatever it is that makes up sweet tea, would you agree with me that the concentration is the same in these two containers? Okay, whatever I poured out of my initial container is going to end up in the smaller container. So the concentration of sweet tea is the same, assuming we don't pour water in or assuming we don't add extra sugar or something like that. Assuming we just take it straight out of the tap here, we have the same concentration of tea in the large container as we have in the small container. All right, so the concentration is the same. What is not the same is the number of moles, but the number of moles per liter is the same. If we were to scale this up to a liter and take 1 liter out of this, we'd have the exact same thing. That's the idea behind concentration. The moles per liter might be, is the same. The number of moles is not the same. There's going to be less in here than there is in here because the volume of this is bigger, but the moles per liter is exactly the same. That's a key foundational idea in understanding why we use a concentration unit. In other words, it doesn't matter how much of the stuff we have, the concentration will be the same, whether it's a small glass or whether it's a 5-gallon container. Okay, let's take a look at a couple of problems then. We'll start with this first problem. How many moles of HCl are there in 27.5 milliliters of a 10.7 molar HCl solution? So I'm just going to put a little star next to this one. This is a really classic example of a molarity problem. This is a really important one you need to learn how to deal with. And the key to dealing with this is recognizing the following. The number of moles of a material is equal to the molarity of whatever that is times the volume of whatever that is. And we can use units to help us understand this. This is moles of solute divided by liters of solution. If I multiply that times liters of solution, those units are going to cancel out, and that's going to leave me number of moles of solute. Okay, so when you have a problem, problem involving molarities, if you have a volume and you have a molarity, you can find the number of moles. A common mistake that a lot of students make is they'll see the HCl, they're trying to find the number of moles, and they'll jump to trying to find the molar mass of HCl. Notice if you have a volume and a molarity, you do not need the molar mass. Okay, that's an important concept right here, is if you have a volume and a molarity, you can immediately find the number of moles. So, armed with that piece of information, I'm going to say the number of moles of HCl is equal to 27.5 milliliters. And the only trick, wouldn't really call this a trick problem, but you always need to convert this into liters, just because molarity is defined in liters. So we've got milliliters canceling milliliters, and then I'm going to say times 10.7 moles, and I'm going to write this unit out completely just so you can see the units canceling. Moles HCl for every 1 liter of solution. So liters of solution is going to cancel liters of solution, so that is going to leave me with 0.294 moles of HCl. Okay, This is a classic problem right here. And you should really get comfortable doing this. So if you see a problem where it's saying how many moles of something, some solution, if you see a volume and you see a molarity, you should immediately think, okay, good. All I need to do is multiply them together. Just make sure you get that volume into a units of liters, and it's a one-step process. Volume times molarity gives you number of moles. Okay, second type of problem. What's the volume in milliliters of a 7.25 molar NaCl solution that contains 1 moles of sodium chloride? So what this is saying is, if I had a liter of stuff, if I had a liter of sodium chloride, there would be 7.25 moles in that liter. But what if I only want a mole of stuff for my reaction? Well, I don't need a liter, I need less than a liter. So I need to figure out, using the molarity, I can calculate what volume I need to actually get 1 mole of sodium chloride. So here's how we set that one up. So I want to find volume of NaCl needed, and that's going to equal to 1 mole is my starting amount. 1 mole NaCl, and now this is also a one-step problem. Every 1 liter of solution has 7.25 moles of NaCl. So moles NaCl is going to cancel moles NaCl, and that is going to equal to 0.138 liters of solution is what I need. Now it's asking for it in milliliters, so now I just need to say 0.138 liters times 1,000 milliliters for every 1 liter. Liters going to cancel liters, and then that's going to equal to 138 milliliters of solution. Okay, what does this mean? What is the significance of this? What this means is, if I had a liter container of this solution, this 7.25 molar NaCl solution, if I measured out 138 milliliters of that solution, that would contain 1 mole of sodium chloride. Or if I happen to have 138 milliliters, that's the same analogy we used here with the sweet tea. Instead of having 5 gallons, if all I have is 138 milliliters, I would have 1 mole of the sodium chloride in there. Okay, that's not quite as common a calculation to do, but you should understand that with a one-step calculation, you can find the number of moles you have if you're given the volume and the molarity. All right, and then the last thing is, how many grams of sodium hydroxide are needed to produce a certain concentration solution? This is another really common type of problem, and this is one you might have to deal with in lab. Okay, so put a little star next to this one. Let's read it again. How many grams of sodium hydroxide are needed to produce 50 milliliters of a 4.75 molar solution? Okay, so this is actually a 2-step problem, and I'm going to outline what the steps are. So step 1 is to find the number of moles of NaOH that you need. And then step 2 is to convert that NaOH, convert the moles of NaOH to grams of NaOH. And now, in this case, we would need the molar mass, which turns out to be 40 grams NaOH per 1 mole of NaOH. So the only time you need to invoke the molar mass is if you have this kind of problem where it's asking you to make a solution from a solid. Okay, so your default should not be to use the molar mass. It's only if you have a case of this where you have a solid, like sodium hydroxide is a solid at room temperature, and you're trying to make a solution. All right, so let's run through the steps of this. You might want to stop the video and see if you can do this yourself. So let's do step 1. So we're going to find N of NaOH, and you notice that's exactly the same type of problem as the first one. So that one we take the volume, 50 milliliters, times 1 liter per 1,000 milliliters times 4.750 moles NaOH for every 1 liter of solution. This is an identical problem to problem number 1 that we did. So liters cancels liters, milliliters cancels milliliters, and we have moles NaOH resulting, and that comes out to be 0.2375 moles NaOH. Notice 4 significant figures, 4 significant figures. My answer should have 4 significant figures. Okay, so the next step, part 2, this is one you've done 100 times already. Now we want to find the grams of NaOH. So that's just going to equal to my moles, 0.2375 moles NaOH times 1 mole NaOH goes on the bottom, and 40.00 grams NaOH goes on the top. Moles cancels moles. I have my units in grams, so this is going to equal to 9.500 grams NaOH. All right, that's the number, 9.500 grams of NaOH. But what does it mean? What does it mean that I have to 9.500 grams? Okay, let's take a look at the top here in this figure that I included. And this is not for this particular example, this is for a different example, but we can use this for this example. So what we would do is we would weigh out 9.500 grams NaOH, and then we would pour those pellets into a graduated cylinder. Graduated cylinders are designed to have a specific volume. In this case, the one we want is a 50 milliliter graduated cylinder. And what graduated cylinder means is it's got a specific volume already, and then there's a mark on the side of the container that tells you whatever the volume is. The example from the book here is a 1 liter one. The example I'm giving you right now is the same looking device, it's 50 milliliters. And if the thing is, if you pick the correct graduated cylinder, it is good to 2 decimal places. That mark is good to 2 decimal places. So what we would do is we would put our 9.5 grams of sodium hydroxide into the graduated cylinder. We'd fill it part of the way up with water, and then we would completely dissolve this sodium hydroxide. Then what we do is we fill the rest of the way up to the mark, and if you're looking at this from the side, if you're in your lab, you might see this long tube, and there's a little mark on it, and if you look at it from the side, you want to put it so the meniscus comes right to the bottom of that mark. And the best way to do that is to put your eye level with the meniscus, level with the mark on here. So if you put your eye even with it, then you can see where the bottom of the meniscus is. So again, you dissolve it to here, you fill it to the line, then the last step you do is you put a cap on this, turn the thing over several times to shake it up so you have a uniform concentration, and then you have your solution. And this figure says 1 molar NaCl. We've actually made 4.750 molar NaOH. Okay? So, what we did was we found the mass of stuff that we need to measure. That was that 9.500 grams. We used a 50 milliliter volumetric flask. We fill it up, dissolve it, fill it all the way to the mark then, shake it up so it's uniform, and now you've created your solution. In the next video, we're going to talk about dilution and some different dilution problems. So check that one out, and thanks for watching. Bye.